Okay, this is just one final tip for successfully navigating Module 8 on your first attempt. Of course, it's very important that you've learned the new derived rules and equivalences and committed them to memory. As I've said, these are the power tools of propositional logic, and they allow you to prove things that in a very short period that would have taken a very, very long time without them. They don't let you do anything you can't do with just the non-derived rules, but they just let you do things much more quickly. Now, that's not the tip. That's just a reminder. The tip is this. You might have noticed that we don't have a derived rule or equivalence that allows you to do anything with a negated biconditional. Now, there's no reason why we couldn't have created a derived rule for this. Because if you think about this, if you think about the truth table for it's not the case that A if and only if B, or if you think about even better, the tree rule for it's not the case that A if and only if B, right? The tree rule for it's not the case that A if and only if B goes to A and not B, or B and not A. So we could have developed a derivation system where there was a derived rule that said if you have it's not the case that A if and only if B, then you can write either A and not B, or you could write B and not A. Take your pick, right? Now, what I'm telling you might just be annoying. You could just say, well, why didn't you do that then? And the answer is really just that we try to limit the number of derived rules to memorize, especially when there are easy ways of getting around them. So basically, you don't have a negated biconditional rule, and so when you deal with negated biconditionals, you might have to use your creativity a little more than with other rules. Excuse me, with other formulas. So let me just throw a proof at you, and I ask you to stop the video and actually work it out yourself. The proof is it's not the case that A if and only if A, therefore Q. Okay, so give that an honest try before watching the rest of it. All right, so if you struggled with this proof, or maybe you think you actually got it right, but didn't, let me start at the beginning, and that is to remind you that you can't do biconditional elimination on this line, right? Do you understand that? It's very important. This is a negated biconditional, which means that the negation is the main operator, and biconditional elimination is an inference rule, not an equivalence. So if you began like this, there's your assumption, and then you said, okay, on line 2, I'm going to go if A, then A by 1, and biconditional elimination. That is wrong, right? Because the negation is the main operator. So let's take another shot at this. Okay, so 1, it's not the case that A if and only if A, assumption. And, you know, the weird thing is that we're supposed to derive Q, and Q isn't here in the assumption at all. And what that tells you pretty much automatically is that this must be a contradiction, right? And if it's a contradiction, then we need to be able to derive an explicit contradiction from it. Okay, so this is not a contradiction by itself, right? Oh, so when I call it a contradiction, what I mean is it must imply a contradiction. So the crucial insight to do this proof is to say, well, it looks like I'm going to have to aim at a particular contradiction because there's nothing I can do to break down this formula, right? So how do you do that? Well, you've only got one formula, so it looks like what you want to do is derive A if and only if A, okay? In other words, you're going to basically show that A if and only if A is a theorem. So that's very simple, actually. Hypothesis A, right? And what have you just done? You have shown if A, then A, right? So that's just by 2 through 2 conditional introduction. I know it's a little weird, but you should have seen problems like this already where you just are using one line. So if A, then A. So now what can you say, right? Well, now you can say A if and only if A. Now why is that? Well, you have if A, then A, and you also, I know this sounds weird, have if A, then A, right? So that means you have A if and only if A, and so now you can just do 3, very strange, huh? Biconditional introduction. And there's your contradiction, right? We contradicted the original formula. And so now what can we do? Well, what we're going to use is the con rule. Now, if you forgot about the con rule, that's too bad. You could take a roundabout way and do negation introduction. You could hypothesize not Q now, right, for negation introduction. Remember, this was for conditional introduction. And then you could just repeat the contradiction and punch out of your negation introduction proof. But the simple way is just to use the con rule, right? So we just say Q, right? And we say Q because there's now a contradiction between 1 and 4. So 1, 4, con, and we're done. Okay? So it's a very simple little proof as long as you realize that you can't operate. There's no rule that allows you to operate on this negated biconditional, and that in order to find that contradiction, you actually have to build the biconditional. Okay, so that's the key insight. That's something you want to be aware of, and we're showing it to you in this super simple proof. But let's end with giving you a same thing, but just a slightly more complicated proof. Okay, so same basic form. It's not the case that S, if and only if T or P yields, it's not the case that S and if not T, then P. Okay, so again, stop the video, absolutely, and do your honest best to get this one before we continue. All right, so hopefully you got this far. You realize, just as before, there's nothing you can do with the negated biconditional. And so the only thing, and this is a negated conjunction, and so really the thing that makes the most sense is to hypothesize the negation of the conclusion, which gives you this conjunction, S and, if not T, then P. Okay, so a very calming next step is just to say, okay, S by 2 and conjunction elimination, and if not T, then P by 2 and conjunction elimination. And now, right, can you see how we're going to proceed? We're going to build S if and only if T or P. And that's very easy to do because if not T, then P is logically equivalent to T or P, right? How do you show that? Well, If not T, then P goes to not T or P by 4 and material implication. And then you can apply double negation, not negation elimination, right? But the double negation equivalence, which allows you to work on a part of a formula. So now you've got T or P by 5 and double negation. Now, since you've got S and you've got T or P, then you're going to be able to use the conditional introduction rule to get both of your conditionals. So you'll be able to show if S, then T or P, and you'll be able to show if T or P, then S, and that'll ultimately give you the contradiction you're looking for, right? So hypothesize S, hypothesis for conditional introduction. All you do is reiterate T or P, use the reiteration or rewrite rule, T or P by 6 RE, and there you have if S, then T or P. Seems too easy, huh? But this is perfectly legit. So 7 through 8 conditional introduction, and then of course you're just going to do the same thing the other way around. Right, so hypothesize T or P, reiterate S from line 3, if T or P then S, and this gives you what? Now you've got both conditionals, so now you can actually simply write, make sure you do it in the right order, S if and only if T or P. And that's just 9 and 10 biconditional introduction. And now you've got this big old contradiction, right? S if and only if T or P, and not the case that S if and only if T or P. Now, the fun expedient to do here, you can write that all out as a conjunction by conjunction introduction if you want, absolutely no problem. But you can also just write any contradiction you like. You can write, say, R and not R, a very simple one. And why can you do that? Because you can use the contradiction rule here. You have a contradiction, so 113, that's where your contradiction lies, and just use the con rule. So that's just a nice little way of avoiding writing out a big long contradiction. And so there's your contradiction for negation introduction. So now all you have to do is negate your hypothesis. Two through 14, negation introduction, and you're done. Okay, so that's the tip, how to work with negated biconditionals, and there's a good chance you're going to experience one of those on the